Hello everyone. In this video, we will discuss the fundamental theorem of algebra. The fundamental theorem of algebra says that every polynomial equation of the type, let us say x raised to n plus a n minus 1 into x raised to n minus 1 up to a1x plus a naught is equal to 0. So any polynomial equation of degree n with real or complex coefficients has n roots, or we can say that has at least one complex root. So this theorem has a very long and arduous proof in the theory of algebra. We can prove this theorem by using analytic functions of a complex variable also. And in that case, if we develop analytic functions of complex variable, then it just becomes a corollary to Laplace theorem. But now we will prove this theorem, fundamental theorem of algebra. We will prove this theorem now using the fundamental group of the circle. So, firstly, let us state the theorem. A polynomial equation say the equation of the type x raised to n, a n minus 1, x raised to n minus 1, and so on up to a1x, a naught is equal to 0. This is a polynomial equation of degree n. So I'm saying this is a polynomial equation of degree n. That means that is because we are taking the coefficient of x raised to n as 1. So this is a polynomial equation of degree n with either real or complex coefficients. So we have to prove this has at least one real or complex root. So we will prove this theorem now in 4 steps. So in the first step, we will consider a map F from S1 to S1, which is defined by f of z is equal to z raised to n, where this z is a complex number lying in the circle S1. That means we can say z is a complex number whose mod is equal to 1. And we have defined the mapping fz is equal to z raised to n. So in the first step, we will prove that the homomorphism f star, which is induced by f, that is actually injective. So now we take P naught, a mapping from I to S1. Let us say this P naught is a standard loop in the circle S1, which is given by P naught of S. This is e raised to 2 pi iota x. That means cos 2 pi s and sine 2 pi s. So this is the standard loop. Now this is a loop in S1. So it's a path homotopy class that belongs to the fundamental group of S1 with respect to the point B naught, where B naught is the point 1, 0, because this is loop based at point 1, 0. So if we take the image of P naught, image of homotopy class of P naught under the mapping F star, where F star is a homomorphism induced by F. Now F is a mapping from S1 to S1. So F star is basically a homomorphism from the fundamental group of circle to itself. So what is the image of F star at this P naught? So that will be given by F circle P naught, homotopy class of F circle P naught. Now what is this F circle P naught at point S? Now this P naught is a mapping from I to S1 and F is a mapping from S1 to S1. So F circle P naught, that is again a loop in S1, and that is given by e raised to 2 pi iota s raised to n, because f of z is equal to z raised to n. So this is basically cos 2 pi ns sine 2 pi ns. So here we can see that if our P naught is a loop which is given by cos 2 pi s sine 2 pi s, then f of P naught s, that is also a loop which is given by cos 2 pi ns sine 2 pi ns. Means this loop, basically f circle P naught, this loops lifts to the path s goes to ns. So the lifting of this path f circle P naught, that is the path given by s goes to ns in the covering space R. If we take the covering space R of S1, then this is the lifting of this f circle P naught. And because s goes to ns in the lifting of this path, so we can consider that f circle P naught, this loop is basically corresponding to the integer n under the standard isomorphism of the fundamental group of circle with the integers. Because we know that fundamental group of circle pi1 s1 b naught, this is isomorphic to z, the additive group of integers. And this f circle P naught, that gives the correspondence with the integer n in this standard isomorphism. Uh, because if we assume that P naught, that the homotopy class of P naught in this group, that corresponds to 1 in Z, because we know these two groups are isomorphic to each other, and we know this loop, the homotopy class of loop P naught, that belongs to this fundamental group of circle. So if we assume that P naught corresponds to 1 in this isomorphism, then F circle P naught corresponds to N in this isomorphism. So we can assume that F star, the homomorphism F star, is basically the multiplication by n in the fundamental group of S1. So this gives basically multiplication by n to each element of pi1 S1 B naught. So it means it is an injective. It gives the number multiplied by n. So when we take two different numbers in the domain of f star, then we take two different images of these two numbers, because it just multiply by n to both the numbers. So this is basically injective mapping. Now in step 2, we will assume that if we take g from S1 to R2 minus 0, the mapping g z is equal to g z raised to n. So if we define g from S1 to R2 minus 0, again gz is equal to z raised to n, then we will prove here that g is not null homotopic. So in this step, we will prove that g is not null homotopic. Now basically, if we define g from S1 to R2 minus 0 by gz is equal to z raised to n, so this g is basically equal to j star f, where this j, this is inclusion map from S1 to R2 minus 0. So this is inclusion map, because we know f is a mapping from S1 to S1, which maps z to z raised to n. So if we take j from S1 to R2 minus 0, which is inclusion map, so it fixes all the elements of S1. It means g is basically j star f, j circle f. If g is j circle f, and in the first step we have proved that f star is injective, and since we know that S1 is a retract of R2 minus 0, that means there exists a retraction from R2 minus 0 to S1, and J is the inclusion map from S1 to R2 minus 0. So because of this, J star is injective. because we have already proved that if we have inclusion map from A to X and we have a retraction from X to A, then J, the inclusion, the homomorphism induced by J, that is also injective. So in the first step, we have proved F star is injective, and here we have proved J star is injective. And secondly, G is equal to J circle F. So G star is equal to J star circle F star. And both the mappings on the right hand side are injective, J star as well as F star. So it means G star is also injective. Now, if G star is injective, then G cannot be null homotopic, because if G is null homotopic, then G star must be trivial map. But because G star is injective map, uh, so G cannot be null homotopic. This completes the step 2. Now in the step 3, we will prove the special case of the theorem. And the special case is that given a polynomial equation, let us say this polynomial equation x raised to n, an minus 1, x raised to n minus 1 plus a1x plus a naught. And with the restriction on the coefficient of this polynomial equation is given that mod of an minus 1 plus mod of a1 mod of a naught, this is less than 1. So we assume that sum of mods of all these coefficients an minus 1, an minus 2 up to a1, a naught, that is less than 1. So we will prove in this step that this equation has a real or complex root with this special restriction on the coefficients. So suppose this equation has no root. Now here we will prove that this equation has a root lying in B2. So we prove, let us say this is equation 1. We prove that 1 has a solution. Yeah, 1 has a root. 1 has a root in B2. So we will prove it by contradiction. Suppose it has no such root. Then we define a map K from B2 to R2 minus 0 by this equation K of Z. This is Z raised to N, an minus 1, Z raised to N minus 1 up to a1Z plus a naught. Now since we are saying this equation has no root in B2, that means there is no point of B2 where this polynomial equation becomes 0. That means for any z in B2, this z raised to n plus an minus 1 zn minus 1 up to a naught, this is non-zero for all z in B2. So that's why we have defined a mapping from B2 to R2 minus 0. And then we take H to be the restriction of K to the circle S1. Now we are saying that H is a mapping from S1 to R2 minus 0, which can be extended to B2 to R2 minus 0. And since H has such type of extension, that means H is null homotopic. Therefore, H is null homotopic. So now we will prove that G and H both are homotopic to each other. In the second step, we have proved G cannot be null homotopic, and here we have proved H is null homotopic. So if we prove G and H are homotopic to each other, then by transitivity, we get a contradiction, because two mappings, one of them is null homotopic and other is not null homotopic. They cannot be homotopic to each other. So that will lead to contradiction. So now we define mapping capital F, which is from S1 cross I to R2 minus 0, because G and H both are the mappings from S1 to R2 minus 0, and we want to prove them to be null homotopic. So we define mapping S1 cross I to R2 minus 0 by F of ZT. This is z raised to n plus t into an minus 1 zn minus 1 up to a naught. Now firstly we prove that this mapping is well defined. Means firstly we will prove that f of zt can never be 0. Because if it is 0, then it will not be a mapping from S1 cross I to R2 minus 0. So now this is non-zero because of the reason mod of fzt, which is equal to mod of z raised to n plus t an minus 1 zn minus 1 up to a naught, and mod of a plus b is greater than or equals to mod of a minus mod of b, and we know this z belongs to S1, so mod of zn is equal to 1. Now t is an element in the interval I 0 to 1, so that is non-negative, so we can take it outside the mod. So we get this, and this is greater than or equals to 1 minus t into mod an minus 1 zn minus 1 plus up to mod of a naught. Now again z belongs to S1, so mod of z raised to n minus 1 up to mod of z, all these are 1. So this will be basically 1 minus t mod an minus 1 up to mod a naught. And we have assumed that mod of an minus 1 plus mod of an minus 2 up to mod of a naught, this is quantity which is less than 1. So this is basically 1 minus t into a number which is less than 1, and t belongs to the interval 0 to 1. So this number is basically positive. So we have proved that mod of fzt, this is strictly positive, which means fzt cannot be 0. So this is a well-defined mapping, and this is continuous because it is given in terms of polynomial equation. And secondly, fz0, this is z raised to n, and that is equal to g of z, and fz1, this is basically z raised to n, an minus 1, zn minus 1 up to a naught, and this is h of z. So this proves that G is homotopic to H. But we have proved that G is not null homotopic and H is null homotopic. So this is a contradiction. So our assumption is wrong. So we have assumed that there is no root of the equation in the unit ball B2 with this particular condition on the coefficients. So it means this equation 1 has a root in B2. Now in the last step, we will prove the general case. So now we consider the polynomial equation x raised to n, an minus 1, xn minus 1 up to a1x, a naught. So we will prove that it has a real or complex root. Now we choose a number c, real number c, positive, and we substitute this x is equal to cy. And when we substitute x is equal to cy in this polynomial equation, we get this type of equation, cy raised to n, an minus 1, cy n minus 1 up to a1 cy plus a naught is equal to 0. That means if we divide it with y raised to n, sorry, c raised to n, so we will get y raised to n, an minus 1 upon c, and so on up to a1 upon cn minus 1, a naught upon cn. So if we choose c large enough, so that this an minus 1 upon c an minus 2 upon c square, and so on up to a naught upon c raised to n. This is less than 1. So choose the real number c large enough such that sum of these mods less than 1. And we have proved that if we have a polynomial equation with coefficients, these coefficients such that the sum of their mods is less than 1, then that has a root in B2. So now we have this equation, say this is equation 2, such that sum of mods of these coefficients that is less than 1. So by part 3, this 2 has a root, let us say y naught in B2. Then now if this y naught is a root of equation 2, then because we have substituted x is equal to cy to get this equation 2, that means x naught is equal to cy naught. This is a root of given equation. And if y naught belongs to B2 and c is a real number, then this x naught is basically uh, a root in R2. So we have proved the theorem that this polynomial equation that has a real or complex root. And this completes the proof.